Hello, I'm Gabriela and I'm gonna give you a brief introduction for this experiment and a quick brief resume of the materials we used. So, the introduction of this experiment is a fundamental investigation into Newton's second law of motion and the study of uniformly accelerated motion in one dimension. So, the setup we utilized was an air track to create a near zero friction environment by floating a glider on a cushion of air. And this is crucial because it simplifies the analysis by virtually eliminating the resistive force of kinetic friction. So the glider is connected by a string over a pulley to a hanging mass. So the tension in the string caused by the weight of the hanging mass provides a constant net external force acting on the combined system. And the materials we used for this experiment was the air track and our air source, like a blower, we have in the class, the glider, and a triple beam balance used for measuring the mass also.
In this week's lab, we focus on acceleration versus time graphs. The first thing we had to do is weigh the cart that is going to be on the track, and we weigh that in kilograms. We also get the weight already listed on the holder that is going to carry the weight that is going to push or actually pull our card over closer to the capstone measuring device. So once we get the masses for all the three items, we're going to add them all together to get a total mass, and we would use that for our calculation for later. And we decided to put our cart in the middle of the track, and the cart is attached to a string that's attached to the weight. So once we let go of the cart, the weight is going to pull the cart closer to the passport measuring system, and capstone is going to get the data and first create a position versus time graph. And with that, we're going to make a velocity versus time graph. And then finally, we're going to get the acceleration versus time graph. And then we're going to plot 4 points on our graph. 2 are going to be more towards the top, and the other 2 are going to be closer to the bottom of the graph. And with these values, we're going to calculate the velocity, the acceleration, and also our percent error.
This report is on Lab 3. On Lab 3, we use the theoretical value of acceleration to calculate the accuracy of our acceleration measurements. In the beginning, we received 2 questions. Is the statement, friction and air resistance are negligible in our experiment, entirely or partially true? And for our second question, we received, why can we consider a variable negligible? So for our first answer, we decided that it was partially true, because although our experiment minimizes friction and air resistance, they are not entirely eliminated. The effects of friction and air resistance are small and can be disregarded for this experiment. Even though we used a nearly frictionless surface, there is still some friction in the rope and a slight amount of air resistance acting on the glider. For question 2, why can we consider a variable negligible? We can consider a variable negligible when its effect on the result of the experiment is so small that it doesn't really change the end result. Friction and air resistance exist, but they are very small compared to the other forces involved. Their influence is too small to affect the results. For the beginning of our experiment, we got the weight of the glider. We found that the weight was 194.3 grams, which is equivalent to 0.1943 kilograms, while the weight we put on the holder, our weight being 20 grams and our holder being 5 grams. We had both equal to 25 grams, which is 0.025 kilograms. Using this information, we found the theoretical acceleration. We used the equation acceleration equals mass of the weight times gravity over mass of the weight times mass of the glider. Plugging that in, we got negative 1.1183 meters per second squared. This makes sense because as our glider was bouncing back and forth, it was slowing down. During our experiment, we began by creating our first graph, the position versus time graph. We plotted 4 data points to represent the motion of the glider. 2 of these points were located near the highest position on the graph, while the other 2 were placed near the lowest position. Each point represented a specific position on the y-axis and a corresponding time on the x-axis. Using these points, we are able to complete the first table and begin analyzing the velocity. For the first 2 points, the initial position was 0.15 meters at a time of 1.150 seconds, and the second position was 0.49 meters at a time of 1.250 seconds. From these values, we observed a position change of negative 0.02 meters and a time change of 0.1 seconds. Using this information, we calculated the initial velocity to be approximately negative 0.2 meters per second. Next, we used the last 2 points to determine the final velocity. The third point had a position of 0.39 meters at 1.5 seconds, while the fourth point had a position of 0.36 meters at 1.5 seconds. This resulted in a position change of negative 0.03 meters and a time change of 0.05 seconds. From these values, we calculated the final velocity to be negative 0.6 meters per second. Finally, by using both the initial and final velocities, we were able to determine the acceleration of the glider. Our calculations showed that the acceleration was approximately negative 1.408 meters per second squared. This negative value indicates that the glider was slowing down during its portion of its motion.
For our second graph, we created a velocity versus time graph. The velocities were obtained from the plotted points on the graphing program. For this part of the analysis, we focused on the first and fourth data points from our previous graph. The first point showed a velocity of negative 0.2 meters per second at a time of 1.150 seconds, while the fourth point showed a velocity of negative 0.6 meters per second at a time of 1.550 seconds. From these values, we determined that the change in velocity was negative 0.4 meters per second, and the change in time was 0.4 seconds. Using these values, we calculated the acceleration number 2, to be 1.05 meters per second squared. This negative value indicates that the glider continues to slow down over time, showing a constant deceleration pattern throughout this part of the experiment.
Our last graph was the acceleration versus time graph. For this one, we instead used the mean of the total area of the beginning of the graph. We ended up with a mean of 1.10 meters per second squared, which turns out to be our acceleration number 3. Here I've placed all of our graphs together to show you how we were able to use the same plotted points on each of the graph to find our different accelerations. With all 3 of our accelerations and our theoretical acceleration, we are able to put it into a percent error formula. The percent error formula states that to find the percent error, we would use the theoretical acceleration minus the calculated acceleration all over the theoretical acceleration. This will give us our percentage error. We made sure to use the theoretical acceleration of negative 1.1183 for all of the equations. We did this to each one of our accelerations respectively, using negative 1.408 meters per second squared from our acceleration 1, negative 1.05 meters per second squared on our acceleration 2, and using negative 1.10 meters per second squared on our acceleration 3. With this, we were able to see the percentage error. For acceleration 1, we got a percentage error of 25%. On our acceleration 2, we got a percentage error of 6%. And our acceleration 3, we got a percentage error of 1.6%.
Now for the conclusion. In step 4 of the lab report, we had to answer some questions, and these are the answers that we got for them. The errors should be similar due to the equations given, however, due to human error and difference in setup, it allows for errors to be bigger. It also shouldn't be precisely 0 if it can if there's absolutely no fault or error in any aspect of the environment. And our first acceleration was bad, but the next 2 were pretty good compared to our results, so we consider it to be a good all-around experiment. We'd use the same methods as previously. The only difference would be to have more precision in choosing points and how we calculate our rounding, and also choosing the mean area. We chose a wider range than the area of which the points we were allowed to use, and so it made our readings our errors a lot bigger. In this lab, we learned how changes in mass affect acceleration and how to evaluate those changes using percent error and percent difference. By modifying either the hanging or the glider mass, we were able to observe how increasing or decreasing one variable influences the system's theoretical and experimental accelerations. This helped us better understand Newton's second law and the relation between force, mass, and acceleration. The percent error measures how close our experimental results were to the theoretical calculated values, showing the accuracy of our measurements. A smaller percent error indicates that our results were more precise, while larger error suggests that they may have been mistakes or limitations in our setup or data collection. The percent difference, on the other hand, compares 2 values, such as our old and new accelerations, to show how much they differ from each other in relative terms. Any differences or errors in our data could have been caused by several factors, such as friction on the track, inaccurate mass measurements, misalignment of the motion sensor, or human error while starting or stopping the experiment. These factors can alter the measured acceleration and lead to greater percent error or difference. Overall, the experiment demonstrated that even small variations in mass or measurement accuracy can significantly affect the calculated acceleration. Understanding and minimizing percent error and percent difference is crucial in experimental physics because it allows us success through reliability and precision of our data and identify ways to improve future experiments.